So the next thing that I'd like to do is give you a little bit more of an intuitive understanding of the Inf-sup condition. So far we've proven it for an example case. We looked at the case of the Stokes equation where we could actually change the Inf-sup conditions a little bit, and then we obtained the LBB conditions. But so far it's all still a little bit of a vague requirement. And if we compare that again to coercivity, then we actually did have a relatively intuitive understanding of what coercivity meant, namely that this produced a positive definite stiffness matrix. And positive definiteness is something that we're relatively familiar with from linear algebra, but Inf-sup does not have something like that very clearly, at least. Yeah? And in this video I'll actually show you what Inf-sup means from a linear algebra perspective. Now the first thing that I would like to do is draw the connection between Inf-sup and coercivity, because for special cases coercivity is enough, but again the Inf-sup requirements were the necessary and sufficient conditions, which means that for the cases where we have a coercive bilinear form, we should also be able to show that the Inf-sup condition holds. So what I'll do is actually I'll show that coercivity follows from a very special case of the Inf-sup requirement. And that's actually not too difficult. Suppose now coercivity again only makes sense if our spaces for our trial functions and our test functions are the same, right? So the only way that the coercivity really makes sense is if we have x and x for both spaces. So then, suppose that we take the special case where the Inf-sup condition holds for the choice of w is equal to phi. Then what does this say? This says the infimum of the supremum. Well, no, sorry. Then I already made a choice for w, so I'm not allowed to write this supremum anymore. So I'm substituting something in place of w, so then I simply get the infimum of phi in x of b phi over phi x squared. That has to be larger than or equal to some constant gamma, which has to be larger than 0. So I can multiply both sides by what's under the division here, and we get that the infimum of phi in x of b of phi comma phi has to be larger than or equal to some constant times the norm of phi x squared. And that's precisely what the coercivity statement also says. The coercivity statement says that that has to be true for all functions v, which is the same thing as saying that for the minimum case that has to be true, right? So this is going to be the same thing as b phi. It's going to be larger than gamma phi x squared for all phi in x. And that's precisely our coercivity statement here. So again, let me recap what have I just shown. I've shown that if coercivity holds, then also Inf-sup holds. Yeah? And specifically Inf-sup holds for the special case of w equaling phi. Right? We always try to find the relation between w and phi to prove Inf-sup. For the pure advection case, we chose w is equal to the derivative of phi. But for if we have a coercive problem, then we're actually able to prove this for the choice of w is equal to phi. Okay, so coercivity is a special case of Inf-sup for a special choice to prove Inf-sup. Okay, that's one part of what I wanted to talk about. The second part was, again, connecting this a little bit more to the linear algebra side. And I'll do that for the saddle point problems that we saw two videos ago. So if we have a saddle point problem, then we had a problem of this form. Find, and I'll jump straight to the Stokes equation as the principal example, because well, that was one of our prototypical equations, and actually it's also one of the standard examples for mixed problems. So find u and p, that solution pair, in H1D, and I'll actually use zero boundary conditions. So the space of vectors with first derivatives that are zero on the boundary, times L2 0, the functions L2 that have an integral that is equal to 0, such that we have a of u comma v plus b u, sorry, b doesn't matter. I'll write it like this. I'm not sure if I'm being completely consistent with what I've written before, but I think that's fine. And that's going to be equal to some linear form here for all v in h10 d. And the second one is b q u is going to be equal to 0 actually. And that's going to be true for all q in L2 0. So if we were to use some finite element method to approximate the solution UP, now first of all we saw that we have to be very careful with our choices of spaces, but we'll get back to that in future videos. First I want to kind of look at what the matrix will look like then. And that the matrix that you'll find if you do something like that for any choice of finite element approximation space is a matrix that looks like this. Where here we have a matrix A, where here we have a matrix B, and this is going to be the transpose of B, and this is actually going to be a matrix with zeros. So the lower right block of the matrix is going to be zeros. So the matrix A corresponds to the bilinear form A. If you were to use finite element approximation spaces for U and V, then you would get a matrix, and that's going to be A. And then we have B here. And clearly because we have swapped test and trial functions from this one to this one, that's why this becomes now a B transpose. And on the right hand side we would have some force vector F. Let me use a capital F here. F. And on the bottom we have zeros. Yeah, so that's going to be this one. So this is the stiffness matrix and the force vector that we would obtain. Of course I have to write this slightly differently. So we're multiplying this by our solution function for U and our solution for P, so UH and PH. And the result is going to be equal to F0. There we go. So the way you would solve this is you would invert the left matrix, and then you would pre-multiply both sides by that inverted matrix, and that gives you the solution vector is equal to the inverse times the vector on the right. Now, from that perspective, the question of well-posedness becomes, does an inverse of this matrix exist? And if we have a coercive problem, then coercivity was the positive definiteness of the matrix, and a positive definite matrix has an inverse, right? So that was already the end of the proof in that sense, in a discrete setting. Now this matrix is not positive definite, and that's due to that zero here in the bottom right. And again, you could show this by a simple example of any function u being equal to 0 would always produce a 0 value. So that means that matrix is not positive definite, but luckily positive definiteness is not a requirement for invertibility. And again, that has to do with that coercivity is a necessary condition, but it's not a, it's a sufficient condition, but it's not a necessary condition. And Inf-sup, the Inf-sup conditions then were the necessary and sufficient condition, or the sufficient and necessary condition, I should say. And what were the Inf-sup conditions? Again, I'll write them down. So we had two. We have that the infimum of the supremum of. No, let me. Okay, so we had the Inf-sup conditions, but for the special case of a saddle point problem, they became the LBB conditions. Right, that's something that I emphasize. I think that's important that you are aware of that, and make sure that you know that for the oral exam. So I'll jump straight to the LBB conditions. So the LBB conditions are that, still coming from the weak statement here, we have that A of U or V comma V is going to be larger than or equal to some C times V square in the H1 norm for all functions V in. And then we had this special space, right? V, how did I call that? Did I call that V0? Let me scroll up here. Yeah, I think I called this with the superscript 0. You still see that? Oh. Let me move this a little bit. So V0. We'll get back to what that 0 meant again in just a second. So that was the first LBB condition. That's coercivity of that A part of the bilinear form. And then the second LBB condition was again an Inf-sup condition. Inf of P in L2, 0, of the supremum of V in H1 D of B P comma V of the norms of P and V. And that has to be larger than some constant gamma, which is larger than 0. Again, and the norms taken in the relevant spaces. I don't want to get don't want to write too many details here. So these are the LBB conditions. LBB conditions. Ledyshenskaya, Babushka-Bratzy conditions. And again, let me iterate this one more time. These are the Inf-sup conditions for the special case of a saddle point problem. And a saddle point problem was a problem that has exactly this structure. They will have a symmetric problem with a 0 on this block here. That's a saddle point problem. And I'll discuss, I think in the next video, why this is a saddle point problem and when these show up exactly. Okay, so again, we have here a coercivity requirement. Well, that's something that we understood. There was a positive definiteness of this matrix, but now in this funny space, okay, but still it's positive definite. Okay, that's something from a linear algebra perspective we're able to understand. But now again, we have this Inf-sup condition. And I will use this example to help us understand what Inf-sup means. Yeah? Because I think for this example, we can actually get a good, clear understanding of that. So let me be a little bit more careful in the way that I'm writing this set of equations. Because as you can see, we only have now our solution vector left. So what happened with our test functions here? We had test functions v and we had a test function q. Why are they not in this set of equations? Well, that's because the set of equations is actually a little bit simplified already. The original set of equations looked like this. We first have a line vector, a transpose vector with the test functions that we multiply with our matrix, which I guess B and B transpose and zeros, and then A, which we multiply by our solution vector U and P, which is going to be equal to, oh, sorry, that was too fast. Again, a transpose of our test functions multiplied by the solution field. Or the right-hand side force vector. Now, and then the claim was that this has to hold true for all possible choices of test functions, and then we come to the previous matrix statement, right? But this is actually the one that one-to-one corresponds to the bilinear form that we're seeing here, right? Okay. So this is the perspective that I'll use to understand this, because clearly we're going to have to deal with the test functions as well. So they still need to be in my matrix system of equations. Okay. So then let me again rehearse what was this space V0. V0 was the space of all functions v in V, which was h1, 0, d, but then a discrete approximation of that. So discrete approximation of that, such that, yeah, so let me actually not write that. I don't want to write that. That's why I was hesitant for a second here. Yeah, I'm not going to write that. Okay. Under the condition, so such that for all these functions, the only functions that we'll pick are the functions that satisfy that b q comma v is going to be equal to 0 for all q in L2 0. Okay, so these are just this is just a function space, a space with functions from the original space, but only the ones that satisfy this condition. And just to remind you, for the Stokes equation, although this is more general than just the Stokes equation, but still for the Stokes equation, this bilinear form was q times the divergence of v, which means that if this has to be true for all q in L2, then that means that the divergence of v has to be 0, right? So this is essentially all the functions in our space h1, 0, d, so all the vector functions that have one derivative, but that are also divergence free, have a divergence of 0. Okay, so now let's also move this to a discrete representation. So first of all, let me talk about the dimensions of our spaces here. Let me call the length of this vector capital N, and the length of this vector small n. Yeah, because we have more degrees of freedom for our velocity than for our pressure. It also shows because of the sizes of these matrices. So that means that, and let me also now write the space. So this is going to be the discrete space, VH. So that means that the dimension of the discrete space VH is going to be equal to n. And now I'll use Q for the space of pressures. That means that the dimension of QH is going to be equal to the small n. So in this discrete representation, we can pretty much say this is going to be the set of all real numbers of an n-dimensional vector, right? That's this vector, and similarly that's this vector. And this one is going to be R with the small n. That's going to be this vector. So even though this is a space of functions, we can encode each function in this space by just capital N numbers. That's what I mean by this arrow. And that's exactly what we're doing in this discrete approximation. Okay, so then what does this last line in the statement really say? So actually this one is multiplied by that, is multiplied by that. So that means that effectively I have this left side of that, right? Because the other one is 0. So Q times BT times U. So that the lower line here is saying that Q BT. Now I'll write this as transposes, so that we get Q transpose BT times U is going to be equal to 0 for all Q in Rn, which simply means that BT of U is going to be equal to 0. So that is the discrete representation of our original constraint equation. Remember, this was a constraint equation in the sense that it was saying that our solution field U is divergence free. So now we have a discrete representation of that as the matrix system of equations B transpose U is going to be equal to 0. Okay, so now I'm going to make the big assumption, and that's actually going to be the key at the end. I will assume the following. We assume that BT has n, small n, linearly independent rows. Now it can maximally have small n number of independent rows because of the size of the matrix, right? So this matrix is going to be Rn cross big N. So the amount of linearly independent rows and linearly independent columns can at maximum be small n, under the assumption that small n is smaller than big N. So this assumption then means if a matrix has as many linearly independent rows as the smallest side, right, this either the rows or the columns, then that means that B is full rank, it's a linear algebra term, and in this case also n is smaller than or equal to big N. Right, that's an immediate consequence of this assumption. So this is going to be the big assumption. So it has n, small n, linearly independent rows, which means that it's full rank and small n is smaller than big N. Okay. Now let me now start talking about the other space. We talked a little bit about the space Q here, Q, and let me now talk about the space V. So the space for our test functions V and the space for our trial functions U. So again, we're talking about linear algebra here. So we can always write any solution V, which is a vector in R big N, as the sum of big N times coefficients times basis functions. If this basis is linearly independent. Linearly independent basis functions. So the natural choice is always to choose the natural basis, right? The one where we have 1, 0, 0, 0, 0, 0, etc., or 0, 1, 0, 0, 0, 0, etc. But in principle, you'll be able to always write any function v, which is a function, or any vector v, which is a member of R capital N, as coefficients times basis, as long as this basis is linearly independent, right? It doesn't have to be the natural basis of 1, 0, 0, etc. It can also be an arbitrary set of numbers as long as these bases are linearly independent, meaning that you'll not be able to write any one particular basis as a linear sum of the other bases. Yeah? This is relatively basic linear algebra. I hope that you're still somewhat sharp on your linear algebra. Okay, so that means that right now, given this requirement, or specifically given this requirement, and given our assumption, that means that our solution U lies in this R n-dimensional space, but also has n constraints. Now remember, this BT times U, it looks like this. BT times U, and that's got to be equal to 0. So there's going to be how many constraints? Well, there's going to be as many as there are rows here. And those are n, right? So this has n linearly independent rows, which means that there's going to be n linearly independent constraints, right? Every multiplication of a row by u is going to give me a new constraint. So now, how do I write this? So any function v or any function u, I'll stick with v. So now we have n bases for v and n constraints. So that means that we have n minus n possible solutions. So and n constraints for u. Let me write it right. These are constraints on u. So we have n minus n possible solutions for u that satisfy these constraints. And the second part is, of course, that we also have to deal with the upper part of the matrix here. But purely based on the lower part of the matrix, we have now n minus n possible solutions for u. So again, because this choice of bases is relatively arbitrary, I can always kind of subdivide my bases in small n bases that do not satisfy the constraint, and capital N. Okay, I can always write u now in the following way. Let me make this easy for myself. I will write u. Well, maybe I should also have written u here. U can always be written as n minus n let me actually remove the hat from this guy. So these on the top right we had still the original linearly independent bases. And then that means that this one was also not the hat. So that was the original, the natural basis. And now we've changed the basis. So we changed to this E hat, where, so we're going to choose, so where, for I is equal to 1 until n minus n, we have b t e I is equal to 0. Yeah, so these are all the bases that do satisfy those small n number of constraints. Yeah, so essentially we filtered out all the possible solutions that do not satisfy the constraint. Yeah, so now we have a new representation for u in a smaller set of a smaller basis, right? Even though this is still going to be a vector in Rn, so now we suddenly have something that is smaller dimensional. We have n minus this small n. So that means that we are trying to find, or we can say the following about the space Vt, which was equal to V set minus V0, right? V0 was the space of all functions that satisfied that constraint. So in our case, we can write R n set minus all the basis functions that go from E hat I, but now from I is equal to, yeah, okay, so minus all these basis functions. As equal to 1 to n minus n. Yeah, so the space of transpose, the V transpose space is going to be equal to the original space Rn, the original space R big N, minus all our functions that satisfy the constraint. Okay, because again, that was what the Inf-sup condition centered around. So this would be now Q, and this would be Vt. Okay. Okay, so if I have here an n-dimensional, a capital n-dimensional space, and this one is n minus n-dimensional, then that means that Vt is going to be small n-dimensional, right? So these are the remaining functions that do not satisfy the constraint. So for any vector v in that space, I can write v is going to be the sum over these v coefficients times this new basis, but specifically all the ones that are left over. Yeah, so I is going to be equal to n minus 1 until n. N minus 1 plus 1, I think. Yeah, so this is going to be all the leftover bases that do not satisfy the constraint. Yeah, so I'll be able to write any function in that space as a sum over these bases, these leftover bases. So we can also write this as a matrix system of equations as the following. We can now create a small vector v. So these are all our vi's. And our basis we can actually put in a different matrix, which I'll call E hat. Yeah? So this is going to be n by n. No, sorry, I'm in my notes I have this transposed. I don't want to have this transposed now. So it's going to be this. Sorry. So we have n bases e to e. So we'll call this matrix E hat. And I'm multiplying this by only n coefficients, small n, which are the vi's here. Okay. So any function that does not satisfy the constraints can be written by that matrix multiplication. So let me sort of recap here. What was now the answer or the question that I'm trying to answer? Well, the Inf-sup condition, if you remember the way that we talked about this in the previous video, the Inf-sup condition became important for the existence of the pressure. So first we solved for this, the velocity. For that one we needed this coercivity condition, the first one of the LBB conditions. And then with this given velocity, we then solve as a second step for the pressure, and that's requiring that Inf-sup condition. Right? So the Inf-sup condition becomes important for the system of equations Vt b q is equal to Vt times f for all v in that space, the transpose space. And because we used all the test functions that do satisfy the constraints to find our solution for the velocity field, and then we were left with all the functions that do not satisfy the constraint to define our pressure field. Okay, so this is the question that we're trying to answer. Does this have a unique solution for P, our pressure field? Well, what do these matrix multiplications look like? Well, in principle, originally we had a matrix that looked like this. P, B, V. It's going to be equal to V transpose times the vector here. And if that were to be true for all choices of V in the complete vector space R capital N, then this would not be a well-posed problem. And that's very clear because B is not square. Yeah, and you can't invert a non-square matrix. You cannot obtain a unique solution for every possible right-hand side if the matrix is not square. However, the point here now is that we're not looking for all functions or all vectors v in R capital N. We're not doing that. We're looking for all functions or vectors v in R n without that span of all the bases that did satisfy the constraints. Well, we have a nice representation for functions in that space that was precisely this space. And functions in that space could be written like this. So let me now substitute that in place of v here. So we have v transpose, and now I have to transpose that what it says over here. So let me get v hats transpose times E times B times P is going to be equal to, same thing, V hat I transpose times the bases that do not satisfy the constraints times the vector. So what's the dimensions of my vector multiplications here? Well, I have 1 times r small n, then I have r small n times r big N. We have r big N times r small n times 1, right? We have small n number of degrees of freedom for our pressure field. So it can give me a multiplication that ends up with 1 by 1 is equal to r small n, 1 times r small n times r small n times r big N is r big N times 1, which also gives me a 1 result here. And now this one can be true for all v hat I in R. Well, how many? We have small n number of these functions. So I can collect these matrices, right? I can perform this contraction, and that gives me then v hat I t times, sorry, I should be a little bit more careful to keep illustrating the sizes of these matrices properly. So I have a few of those, few of these, pressure. So this is now the contraction of this E and this B. So let me write that B with a hat. That's going to be equal to V hat I transpose times F here, whatever F may be. And again, that has to be true for all VI in R n. So at that point, we're allowed to simply cross out these guys. And now we have B hat times P is going to be equal to F, where this is simply an n by n matrix, this is an n by 1 matrix, and this is also an n by 1 matrix. So, summarizing, the original question of being able to solve this large equation has to do with the positive definiteness of the matrix A. That was the first LBB condition, and some strange requirement that we are trying to understand on B, and that's the positive definiteness of A. Well, that was clear. That's going to give us the solution for U. But what was the other condition for B? What does it mean? Well, that was the condition that's going to give us a well-defined pressure field. And now, after all this rewriting, we understand that that has to do with the invertibility of B. So the invertibility of B somehow has to do with that funny Inf-sup condition. You still see that? Yeah. Divided by the norms. The sup of V and the inf over P. So somehow the invertibility of this matrix B hat corresponds to the Inf-sup condition that we're trying to understand. Now, going through the derivation, we can actually understand when B is invertible. So B, again, is the matrix multiplication of E hat and B. Sorry, B hat is equal to the matrix multiplication of E hat and B. So if we look at E hat, what was E hat? Well, this was a matrix that was comprised out of a bunch of basis functions, a bunch of linearly independent basis functions. Well, not just any basis functions, the basis functions that did not satisfy the constraint, but nevertheless they were linearly independent basis functions. So by construction, E hat is full rank. And we have in and linearly, and this was E transpose, sorry. E hat transpose is full rank. It has in linearly independent rows. By construction, that's the way that we defined that matrix. For B, we also have an assumption. We assumed that B transpose had n linearly independent rows, and thus that B is also full rank and that n is smaller than n. So we have that E hat is full rank and looks like this. And we have that B is also full rank by assumption. And secondly, B looks like that. So now this is something that may be intuitive or not, but something that I don't want to discuss in too much detail. But if you have a matrix multiplication of this form, yeah, so this is the small side, this is the long side where n is smaller than n. And both are full rank. Now we have a small n by n. And this one is full rank, and this one is full rank. Then the resulting matrix on the right hand side is full rank. And that kind of makes sense. We have a matrix with all the information it can contain, full rankness, multiplied by another matrix that contains all the information that it can contain, because it's full rank, and we're multiplying these over the smallest edge. Well, then the result's going to be a small matrix, which will also contain all the information it can contain, namely it is full rank. So now we have a square matrix that is full rank, a square full rank matrix. That is, those are the necessary and sufficient conditions for invertibility. So this is invertible. Now that's a very core concept of linear algebra. If a matrix is square and it is full rank, it is invertible, and any invertible matrix is square and full rank. So this goes both ways, meaning that it is a necessary and sufficient condition. So then coming to the punchline here, what does Inf-sup then this mean? Well, the bottom line here, that is by construction, so there's nothing that's going to tell us extra. But this is the assumption that we made, and that's going to align with the Inf-sup condition. So the Inf-sup condition in a discrete sense means that B is full rank and n is smaller than or equal to big N. That is the discrete representation of the Inf-sup condition. And that's going to end up being going through these steps, the condition that also makes this matrix B hat invertible and hence giving me a certain pressure solution. Okay, so going back all the way to the LBB conditions up top here. The first condition was a coercivity condition. That's something that we could wrap our heads around. That was the positive definiteness of the matrix. That means that the matrix was invertible, but it was not a necessary requirement. The Inf-sup condition now, just as we just concluded, says that that this edge is smaller than that edge. Similarly, that this edge is smaller than that edge, and that B is full rank. And given those two conditions, this saddle point matrix permits a unique solution for U and for P. Yeah, so that's the matrix or the discrete or the linear algebra representation or understanding of the Inf-sup condition. Okay, so that's pretty much all for this video. Let me though emphasize that I do not mean for you to understand every single set of these steps. I would be very happy if you do. I think it's a very interesting theory. I want you to understand the conclusion though. I want you to understand that coercivity relates to positive definiteness of a matrix. An Inf-sup condition is a much less tight condition, but it is a much more important condition. It is the full rankness, and in this case specifically also with the condition that the matrix is a standing matrix rather than a lying matrix. So I hope that sort of shed a little bit of light on what the Inf-sup conditions are about. I think trying to understand this from different angles is always the way that gives you the most insight. So we did a proof, and now we did a linear algebra interpretation. So I hope that's helpful. That's, I think, the last video on the series on the Inf-sup conditions. So now we'll move on to the mixed formulations, and that's where these Inf-sup conditions are so important, because those are the saddle point problems that we've been using as examples up to this point. Okay, thank you for your attention.